Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we're going to begin our analysis of vector fields and line integrals. As an example of a vector field, suppose we have a stream. And the water flows maybe rapidly through narrow regions and more slowly through other regions. It changes direction, changes the speed. At each point in the stream, we have a little velocity vector associated at that point. It's as though we have a function that maps some domain that is contained in Rn, the points in space, and outputs vectors perhaps in some other vector space, Rm. This will culminate the discussion that we gave earlier in the course. We mentioned that in Calculus 1, you dealt with real valued functions of a real variable. We went on and described vector valued functions. They ended up being curves. Then we looked at functions with a domain in Rn that output real numbers. When n is equal to 2, you have what is called a surface embedded in R3. If n is bigger than 2, you have a hypersurface. And then now we're going to look at functions where you have a vector input and a vector output. You're associating a vector in the range space with a point in the domain space. There are many examples of vector spaces. You have a massive object. The force of gravity gives you a vector field. Gravity gets weaker as you go out, but it seems to point towards the center of mass. Since the vectors that are associated with each point in space are force vectors, this sort of vector field is called a force field, of which we can think of several kinds. Other sorts of vector fields might be the electric field and the magnetic field of the theory of electromagnetics. At each point around a charged particle, there is an electric field. And if you have, say, a current in a wire, you have a magnetic field that cycles around. There are fields called central fields. To describe a central field, let's first describe the position vector of objects in space. Suppose a position vector has coordinates x, y, and z. Of course, the norm of the position vector is the square root of x squared plus y squared plus z squared. A central field is a vector field of the form some function that only depends upon the norm times the position vector. In this way, the central field will always be some rescaling of that position vector. So if you choose, for instance, some point in the plane, the position vector points towards this point. At that point, you're going to assign some rescaling of the position vector. At another point over here, some rescaling. Another point over here, some rescaling. And so the fundamental element of a central field is it points either away from or towards the origin, depending upon whether or not the function f is positive or negative, but will only depend upon the magnitude of the position vector. A special type of central field is an inverse square field. An inverse square field is a vector field of the form a constant over the norm of the position squared times the unit vector r over the norm of r. As you can see, we're looking at a unit vector pointing away from the origin. We've normalized the position vector, and multiplying by some constant, could be positive or negative, divided by the norm of the position vector squared. In other words, every inverse square field is of the form k over the norm of r cubed times the position vector r. Sometimes you'll see these written as k over the norm of r squared times some other thing, say some unit vector where u is position over the norm of the position. There are two prototypes that I would like you to be aware of. First, suppose I have the vector field that for each point xy it outputs the vector xy. At the origin it outputs the 0 vector. At 1, 0 it outputs the vector 1, 0. At the point 1, 1 it outputs the vector 1, 1. At 0, 1 it outputs 0, 1. And you can see all the way around what happens to this vector field. These vectors point directly away from the origin. The farther out you go, the bigger these vectors get. Always pointing out, away from the origin. How would you describe this vector field? Would you say that these vectors in this vector field diverge? They're all kind of divergy, if you will. That's kind of characteristic of this first prototype. There's a second prototype that I would like for you to be aware of. Suppose at each point xy we output a vector negative y x. Let's see what these vectors look like. Of course, at the origin you output the 0 vector. But at x equals 1, y equals 0, you end up with 0, 1. At x equals 1, y equals 1, you get negative 1, 1. At x equals 0, y equals 1, you get negative 1, 0. At the point negative 1, 1, x is negative 1, y is 1, both coordinates are negative 1. At negative 1, 0, you get 0, negative 1 output. And so on, all the way around. How would you describe these vectors? Farther out you go, the bigger they'll get, but they'll keep cycling around the origin. How would you describe that? To implant a word in your brains, could you say that this vector field has some curl? I'd like to define a special kind of vector field. A vector field F is called conservative if there exists a scalar field, a scalar valued function, little f, such that the vector field big F is the gradient of little f. In this case, little f is called a potential function. It's the scalar potential. Recall the gradient was the vector of partial derivatives, however many coordinates you have. From now on, I'd like for you to think about the symbol del, or nabla, to be like a vector operator. Of partial derivatives. If you apply this to a scalar valued function f, you end up with the gradient. Thinking of our two prototypes, which of our prototypes is conservative? Is the first prototype conservative? Well, if it is, then it's of the form the partial derivative of f with respect to x equals x, and the partial derivative of f with respect to y equals y. If df dx is equal to x, then the potential function must be the integral of x with respect to x. That would be x squared over 2 plus something that is constant relative to x, but not necessarily constant relative to y. We'll get an arbitrary function of y. If df dy is equal to y, that implies f is also the integral of y with respect to y, which is y squared over 2 plus an arbitrary function of x. These must both be true. Is there a way to reconcile them? Surely, x squared over 2 must be lurking in C2, while y squared over 2 must be lurking in C1. If we make f equal to x squared over 2 plus y squared over 2, maybe plus any arbitrary constant, then the gradient will be the vector of partial derivatives. The partial derivative of this f with respect to x is x, and the partial derivative with respect to y is y. So there isn't just one potential function. There are infinitely many, and they differ by a constant. We deduce then that the vector field xy is conservative. The potential function is x squared over 2 plus y squared over 2 plus any constant. Now let's examine the second prototype, negative y comma x. In this case, if this vector field is a gradient of a scalar potential, that will imply that the partial derivative of the scalar potential with respect to x is minus y, and the partial derivative of the scalar potential with respect to y is positive x. Let's check something real quick. What happens if we take the derivative with respect to y and x? Taking the derivative of df dx with respect to y gives a value of minus 1. On the other hand, the second order derivative with respect to x and y requires that we calculate the derivative of x with respect to x. That gives 1. These partial derivatives are not equal, contradicting Clairaut's theorem. We deduce then that no scalar potential f exists, and that means this vector field is not conservative. So the first prototype was all divergy and no curly. It was conservative. The second one was all curly and no divergy, and it was not conservative. Are inverse square fields conservative? Recall that inverse square fields were fields of the form k over the norm of r cubed times r, absorbing the normalization for the factor r into the coefficient. That means inverse square fields are of the form kx divided by x squared plus, let's do this in the case of, say, r3. We'll have similar coordinates for y and z, but the first coordinate is of the form kx over the quantity x squared plus y squared plus z squared, all to the power of 3/2. Is this a gradient field? Is it conservative? Let's see. In order to be conservative, we would have to have df dx equals kx over x squared plus y squared plus z squared to the power of 3/2. Can we integrate this and figure out the scalar potential? We must in fact have f is the integral of kx over x squared plus y squared plus z squared to the 3/2 dx. This requires, of course, a substitution. Where du is 2x dx. We have the x, but not the 2, so we'll divide the 2 off. The k can be brought out of the integral. We get k divided by 2 times the integral of u to the minus 3/2 du. That's k over 2, u to the minus 1/2 times negative 2, plus something that does not depend upon x, an arbitrary function of y and z. You can see that the 2's go away, and we get minus k divided by the square root of u. But the square root of u is the norm of the position vector. Of course, to within a constant relative to x, but perhaps something that depends upon y and z. But by symmetry, I think you can see that this potential function will do with a genuine constant. By symmetry, I think you can see that if the scalar potential is minus k over the norm of the position vector, we already know that implies that the partial derivative of the potential with respect to x is kx over x squared plus y squared plus z squared to the 3/2. But by symmetry, we'll also have df dy is ky over the same denominator, etc. It follows then that all inverse square fields are conservative. This treatment is a little bit different from physics. The negative that you see here is the reason that in physics they choose minus F to be the potential, and in that case it will equal the potential energy. As another example, suppose I have F equals, say, 4x, 6y. Is this conservative? Let's find out. if there is a potential function where the gradient is equal to this vector field, then the derivative of the potential function with respect to x must be 4x. That means that when you integrate the partial derivative with respect to x, you will get f. So when you integrate 4x with respect to x, you get 2x squared plus an arbitrary function of y. Similarly, we have to have the partial derivative of the potential with respect to y equals 6y. That means f must also have a representation of the integral of 6y with respect to y, which gives you 3y squared plus an arbitrary function of x. Reconciling these two answers, you get a potential function of 2x squared plus 3y squared plus an arbitrary constant. In other words, since the potential function exists, this vector field is conservative. There is an easy test for whether or not a vector field is conservative. Suppose a vector field has coordinate functions m and n. And let's also presume that m and n are C1 functions. To be C1 means that their derivatives exist and are continuous. And we want these to be C1 on an open set disk. Then f is conservative if and only if the following condition holds. The partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So this is a characterization of conservative vector fields in R2. This is only for vector fields in R2. There will have to be another test for vector fields in R3. This is an if and only if theorem, so we technically have to prove this in both directions. We'll begin with this direction, where we assume that the vector field f is conservative. That means that f is a gradient field. It's the gradient of a scalar potential. We deduce then that df dx is equal to m, in which case the second order derivative of f with respect to y and x is the derivative of m with respect to y, often denoted by m with a subscript of y. In addition, the derivative of f with respect to y must equal n, and that means the second order derivative of f with respect to x and y will be equal to the derivative of n with respect to x, or in x. By Clause's theorem, these two must be equal. The proof in the other direction will have to come later, after we develop a little more mathematics. So we'll call the theorem quits for now, but we'll come back to it. For now, I'd like to check out the last example. In this case, m is 4x, and n is 6y. my is the partial derivative of m with respect to y. Well, that's 0. And nx is the partial derivative of n with respect to x, which is also 0. we deduce that this vector field is conservative, which we've already shown by explicit construction of the potential function. Back to our prototypes. For the vector field x, y, m is x, so my is 0. N is y, so nx is also 0, and therefore it is conservative. For the vector field minus yx, m is minus y, so my is minus 1. N is x, so nx is 1, and we do not get equality. Therefore, this vector field is not conservative. Let's look at the vector field x squared y, xy. Is this vector field conservative? My in this case is x squared. Nx is y. These are not equal, so the vector field is not conservative. As another example, consider the vector field 2xy, x squared minus y. In this case, my is 2x. Nx is also 2x, and therefore it is conservative. Now that we know that it is conservative, let's find the potential function. To do that, keep in mind that we integrate m with respect to x. That gives us x squared y plus an arbitrary function of y. Alternatively, we have to integrate n with respect to y. That gives you x squared y minus y squared over 2 plus an arbitrary function of x. We need to reconcile these two answers because they both must be true. Minus y squared over 2 must be lurking in the function c1 of y. It follows then that the potential function is x squared y minus y squared over 2 plus an arbitrary constant. We've introduced a new operator. At least, it looks like this in R3. In R2, you would ignore the last coordinate. We can also write this as dx, dy, dz. Just because we're lazy, we'll do this for short. We're going to introduce two new operations. We already know that the gradient can be expressed in terms of this operator. Grad of f is del applied to a scalar potential f. There are two more operations we're going to introduce. First, the divergence of a vector field. Let's suppose the vector field has coordinates m, n, and p. The divergence is denoted by either div of f or, more commonly, del dot f, and defined by the following. The divergence of the vector field f is, because I said so, del dot f. It's done exactly as you might expect. It's the partial derivative of m with respect to x plus the partial derivative of n with respect to y plus the partial derivative of p with respect to z. If I have the vector dx, dy, dz, and I'm dotting that with m, n, p, you might expect to get exactly this expression. Let's calculate the divergence of our two prototypes. First, the vector field x, y. The divergence of this vector field is dx, dy dotted with x, y. That gives you the derivative of x with respect to x plus the derivative of y with respect to y. Notice that the outcome is a scalar, as you might anticipate, since the divergence involves a dot product. We get a positive divergence for this vector field. This vector field was pointing out in all directions. Let's look at the other prototype. The other prototype was the vector field minus yx. If you take dx, dy, and dot it with minus yx, you get 0 plus 0. No divergence at all, which you might anticipate since this vector field was all curling, no diverging. There's another operation that I'd like to define. It's called the curl. The curl of a vector field M, N, P, and this particular definition only applies to vector fields in R3, because the curl is only defined in R3. First of all, it could be denoted by CURL of F, but more commonly it's del cross F. And it's defined exactly as you might anticipate. The curl of the vector field F is the determinant of I, J, K, dx, dy, dz, m, n, p. You can see then that the curl is going to be py minus nx, comma. We'll put a preemptive minus for the negative on the middle cofactor. Px minus mz, comma, nx minus my. Let's look at our prototypes. We can extend these by putting a 0 in the last coordinate. The curl of the first prototype, you put the coordinates of the del operator in the second row, and then the coordinates of the vector field in the last row. We'll get 0, 0, and then 0. This vector field seems to have no curl. After all, wasn't it all divergence, no curl? Now let's look at the other prototype. And we'll squeeze a 0 in there as the last coordinate. Let's calculate its curl. I, J, K are always on the first row of the curl, and always dx, dy, dz on the second row, and then the coordinates of the vector field on the third row. We get 0, 0, and now we get 1, minus -1. We get a non-zero curl. In fact, if we have the x and y coordinates like this with the z coordinate poking out this way, remember that our vector field went around like this. If you take your right hand and curl your fingers in the direction of the rotation of the vector field, your thumb will point in the direction of the curl. That's called the right hand rule. We're going to make the following definition. A vector field F is called irrotational if the curl is the zero vector. Our first prototype was irrotational. It was also conservative. Suppose you have a vector field that is conservative, which means it's the gradient of a scalar potential. I would like to look at the curl of such a vector field. The curl of a gradient of a scalar potential. What does that look like? Well, we're taking the curl of a vector field df dx, df dy, df dz. That should be I, j, k, dx, dy, dz for the coordinates of del. And then let's write these as fx, fy, fz. We have then fzy minus fyz. Well, Cal3Mod's theorem says that that's 0. Then we get minus fzx minus fxz, which again is 0 by Cal3Mod's theorem. And the last coordinate is fyx minus fxy, and that again is 0. We deduce that if a vector field is conservative, then it is irrotational. It's even more interesting than that. The theorem is a sufficiently smooth, let's say C1 vector field F is conservative if and only if it is irrotational, meaning the curl of F is the zero vector. So being irrotational is a characteristic of conservative vector fields. And remember, all inverse square fields are conservative. You can see then that the gravitational field, all pointing in a kind of negative divergence, no curl on the gravitational field. Gravity is irrotational. Also, Coulomb fields are irrotational because they are inverse square fields and hence conservative. The magnetic field, on the other hand, has a lot of rotation to it. It will have non-zero curl and will not be conservative. You can always tell just by looking at the vector field whether or not it's conservative, because if it has rotation in it, it's not conservative. For example, if you've ever seen tip vortices off of a wing, little eddies of air cycling at the end of an airplane wing, that cycling of the air is an indication that the vector field of the wind coming across that wing is not conservative. The same is true when you strike an oar through the water and make little eddies in the current. Those little rotational fields imply that the vector field is not conservative. There's something going on there that is not a conservative process. Conservative vector fields are irrotational vector fields. We have the proof in one direction already. If the vector field is conservative, then it is irrotational. The proof in the other direction, if the vector field is irrotational, then it is conservative. We'll have to defer to later. We have more theory to develop first. Suppose I have the vector field 2xy, x squared plus z squared, and then 2yz. Is this vector field conservative? Let's calculate its curl to find out. We'll have I, j, k, dx, dy, dz, 2xy, x squared plus z squared, and then 2yz. We'll have 2z minus 2z. In the middle coordinate, we'll put a preemptive minus for that negative on the middle cofactor. And then we'll have 0 minus 0. Well, it's 0 anyway. And then 2x minus 2x. We get the 0 vector, which means this vector field is irrotational and hence conservative. Is there an opposite to irrotational? Sure. A vector field F is called solenoidal, similar to a solenoid, which is a round-up foil electrical component. It's solenoidal if the divergence of F is the zero scalar. If you have no divergence, only rotation, then only curl, the vector field is solenoidal. Does this really make sense? It only makes sense if rotation and divergence are the only two things that can really happen to a vector field. Fortunately, we have something called the Helmholtz Theorem. To understand the Helmholtz Theorem, there's one more thing I'd like to show you. Let's suppose that F is the vector field M in P. The curl of F is then going to be I, j, k, dx, dy, dz, M in P, which you can see is dy minus nz, and then minus parentheses px minus mz, comma, nx minus my. What I'd like to do next is calculate the divergence of this curl. To calculate the divergence, we take the derivative of the first coordinate with respect to x. Then we add the derivative of the second coordinate with respect to y. And then we add the derivative of the last coordinate with respect to z. What do you get when you simplify this? Here we have pyx and then minus pxy. By Claraut's theorem, these terms will cancel. we have minus nzx, but here we have positive nxz. So again, the equality of mixed second-order partials requires that those terms cancel. Minus minus makes plus mzy, and here we have minus myz. Those terms must also cancel, leaving us with 0. We can see that any time a vector field can be expressed as a curl, then that vector field will be divergence-free or solenoidal. The Helmholtz theorem goes like this. If F is a C1 vector field, satisfying two nice properties. The first nice property is that in the limit, as the position vector goes to infinity, the divergence of the vector field is 0. And in the limit, as we go out to infinity, the curl is the 0 vector. Then there exist two potentials. There exists a potential function little f and a vector potential. We'll call this vector potential g, such that the vector field f may be decomposed into two terms. The first term is the gradient of the scalar potential. This part is conservative. It is irrotational. The second part is the curl of the vector potential. The second part is divergence-free. It is solenoidal. What Helmholtz theorem is telling us is there are only two things that can happen. You can always decompose any vector field into two parts. The first part has all of the divergence and none of the curl. And the second part has all of the curl and none of the divergence. One of those two parts might be identically 0. If the potential function is identically 0, then the vector field is purely solenoidal. If the vector potential is identically 0, then the function is purely conservative and irrotational. If you can describe the divergence and the curl of a vector field, then you can pretty much describe everything about that vector field. That's why Maxwell's laws have the form they do. And Maxwell's laws describe the divergence and the curl of both the electric and the magnetic field. 4 equations. That's because if you can describe the divergence and the curl of the electric and the magnetic fields, then you've described everything they do. This is due to Helmholtz's theorem. You can see that Helmholtz's theorem is pretty important. I'd like to codify as theorems two things that we've recently shown. First of all, if I calculate the curl of a gradient, I will get the 0 vector. Every conservative vector field is irrotational. Also, if I calculate the divergence of a curl, I get the 0 scalar. If you have any vector field that is expressible as a curl, will be divergence-free and hence solenoidal.